to Math Monday on a whatever day. My name is John Belkowitz, and here I'm talking to you about concrete failure, the type of failure that it is and why it happens at an atomic level and how it goes all the way up to a macroscopic level. With Math Monday, what we want to talk about here is brittle materials. Now, as it stands, concrete is like a ceramic-like material. Now, when I say ceramic-like, I'm not saying it is ceramic. I'm using that hedge phrase to say it is similar to that material, but when it comes down to it, concrete is not very ductile. We know this, that in many different books and a lot of different research, concrete is talked about excessively, that it can't handle flexural, tensile, or shear stresses very well. But more importantly, when we see concrete fail, that hydrated cement matrix, it goes through, especially the higher strength concretes or grouts, a certain type of cleavage or brittle type failure. And when we look at it, we see this cleaved or this brittle type failure has a very smooth surface to it compared to a more ductile failure that has a rougher surface to it. And when we look at it, when we look at a crack, and this is a rudimentary representation of a crack, we have our crack length A and our distance in front of the crack tip R, and that is all used to determine the local strength. And as it turns out, ceramics have very high yield stress or strength. That being said, because they have a very high yield strength, they also have very low plastic deformation. And we look at the localized stress at that crack tip, it is much higher than the ideal strength of that material. And when we have that localized stress, what we're effectively doing is tearing apart the interatomic bonds. Then that crack spreads so that it tears apart the interatomic planes like you see here in this rudimentary drawing. So first it's tearing apart the individual interatomic bonds, but then it spreads over to the planes until we have that smooth surface or that cleaved surface at an intermolecular space, but then that also translates back up to the macroscopic, and that's why we see that smooth surface with our more brittle material like ceramics, glasses, and even concrete. So I mean that's the theory behind it, and that's how we go from the microscopic up to the macroscopic. But this is that stress that I was talking about. You have this localized stress which is right in front of our crack tip, and that's based on the induced stress of the material plus another factor which takes into account that stress times the square root of our total crack length divided by 2 times our distance in front of the crack where our energy is going to have an impact on that brittle material. So yeah, there's more information about that. This wonderful book by Michael Ashby. This was a focus of my master's work, and how different materials added to concrete can make it a more brittle material and allow for these interatomic bond breaking and then those interatomic plane breaking that give us that brittle failure or that cleavage. So if you have any questions, any concrete concerns, don't forget to shoot them over to us. Like, subscribe, go concrete, beat asphalt. Y'all have a nice night.